Today we're going to start talking about the stars in our galaxy, what types of stars are out there, and in particular how we know their distances. And then in further discussions we're going to get into some of this in more detail and how we classify stars and what those classifications actually mean. So just some credits first all. Let's consider this field of stars. There are lots of different stars in here, but I'll tell you that they're all approximately the same distance from us. They're all on the order of about maybe 15,000 light years, give or take a few thousand light years from us. This is the part of the Sagittarius star field in the Milky Way. But you notice that there are lots of differences in these stars. So my question is, what aspects of stars do you believe will determine how long the star will live? So also think about what aspects of a star determine its brightness and its color. Remember, all of these are on the order of the same distance from us. So it's not just, oh, the closer ones are brighter, the farther ones are dimmer. It's not like that because they're all about the same distance. So take a minute to pause the video and write down what aspects of a star you believe will determine its brightness and color. And here's another kind of zoomed in part of same star field taken with the Hubble Space Telescope. So again, pause the video and write down what you think are the aspects of a star that determine its brightness, color, and how long it has left to live. Okay, so if you've written those down and you've unpaused the video, let's see if you got it right. There's actually only one big factor, and that is the star's beginning mass. Now, its beginning mass determines also really how long it's going to live, and given that these stars probably formed at different times, the age is also going to be important in this. So main things are its mass and its age, and in particular what determines how a star will live its life is the mass that it had when it formed. That's something that we're going to explore in a lot more detail as we get into further discussions in the rest of this unit. Here is a star called VY Canis Majoris. It's a red hypergiant, basically a really big version of a red supergiant that's blowing off its outer layers. It's one of the largest known stars. If you replaced our Sun with VY Canis Majoris, then its outer layers would go past the orbit of Saturn. So here is a nice image of a red supergiant star, V838 Monocerotis, and it has had a big flare-up that occurred a couple of decades ago, and that kind of lit the way to allow astronomers to see the environment around it. So we'll get into discussing this particular star in a future discussion. And this should look familiar to everybody. It's been on the constellation quizzes a lot. You have the constellation of Orion. And something that I've also mentioned, the 15 brightest stars in Orion are all going to explode sometime probably in the next 10 million years or less. So, of course, you've heard a lot probably in the news lately about the star Betelgeuse in the shoulder of Orion over here, but also Bellatrix, Rigel, Saiph, Mintaka, Alnilam, Alnitak, the stars in Maesa, the 4 brightest stars in the Orion Nebula, this star right here, Sigma Orionis, as well as a lot of these other stars. They're all going to explode. So the entire area in Orion is still part of this big, vast, giant molecular cloud, the central part of which is the Orion Nebula, M42. So, as we've seen in a number of these pictures, stars come in a variety of shapes, so to speak, sizes and colors. Now, by shapes, it's like, well, they're all spherical, but some of them are kind of blowing out part of their outer envelopes and that sort of thing, so it makes at least the outer part of them non-spherical. So we're going to examine the variety of stars in more detail and what these properties actually tell us over the rest of these discussions. So some of this we're going to skip through very quickly because a whole lot of this is review. So on a typical dark night you can see several thousand stars, but these things are many distances from us. They just happen to be, generally speaking, the brightest of the stars that are out there. In other words, the stars that you see in the night sky are not a good representation of the general population of stars that are out there. The vast majority of stars in our galaxy are quite a bit dimmer than our sun. In fact, the closest star to our sun is way too dim to be seen without good binoculars or a telescope. So, just get an idea of the density of the stars in what we call our solar neighborhood, within like 16 light years of our sun. Well, there are 60 of those. So that within 16 light years, just do your volume of a cube, 4/3 pi r cubed. That gives you about 17,000 cubic light years. So that gives you one star for every 290 cubic light years. And just doing some rounding here, taking the cube root of 290, we find that the average distance between stars is about 6.6 light years. So the closest star to our sun is Proxima Centauri at 4.24 light years, and we'll have more to say about that soon. Now, how do we know these distances? Well, it turns out most of the closest distances we can determine directly. So again, a lot of this is review. I'm going to skip through this, and if you need to pause the video, then pause the video, but a lot of this I'm just going to skip through. But we know the distance from Earth to the Sun real accurately. We know how much a light year is, and we know how long an astronomical unit is in terms of light years and converting to light minutes. And we can use triangulation to determine distances in more detail. So you have points of view that are spaced apart, that see an object from different angles, and based on how the background appears with respect to the foreground object, you can make those comparisons and determine distances. So again, a whole lot of this is review, so I'm going to skip through, and you can slow down if necessary. So here is where we need to slow down and give a little bit more explanation. So how triangulation works, at least in terms of the small angle approximation, what you do is you have some background object, like say a mountain or something like that, and you measure the angle from one of your stations to the object, and then you do the same thing from the other station. And you also very carefully measure the distance between your stations. And based on that, you can use just triangle trigonometry to determine the distance to the object based on these angles, based on the distance between your observation posts and the angle that is made between them. The idea is that you try to make your observation posts kind of perpendicular to the line of sight to the object, so that this ends up being an isosceles triangle. Now, as Earth goes around the Sun, well, the closer stars shift a little bit back and forth depending on the time of year. And the distances to the nearest stars, again, are so far compared with the size of an astronomical unit that even as we move around the Sun, we're not really getting closer to or farther from the star to any measurable extent. Remember, an astronomical unit, the average distance between Earth and the Sun, well, there are about 63,000 astronomical units in 1 light year, and the closest star to our Sun is over 4 light years away. So we're talking about over 250,000 astronomical units when you end up doing the math. So shifting back and forth near to far by 1 astronomical unit, that's not going to change our distance to that star significantly. What we really care about, therefore, is just the angle of the change. In other words, how that star's position in the sky shifts relative to background galaxies. In other words, we really can assume that this is a perfect isosceles triangle when we make this type of measurement. So this becomes just a practice in geometry. Based on how the star shifts, well, shift happens, so knowing your shift, you end up plugging this into a formula. And it turns out that this is something that could have been determined even by ancient people. Ptolemy was able to use this type of formula to discover the distance to our moon. He got it correct within about 3%. Remember, Ptolemy is the person who gave us our idea of how the various celestial bodies move around Earth, at least so he thought, and that was the paradigm for about a millennium and a half. Now, we've also mentioned how ancient Greek philosophers considered the possibility that Earth went around the Sun, but they discounted that because they could not detect parallax. In other words, the stars did not appear to move. It just turns out detecting parallax is really hard. Again, this is all review, so if you need to slow down, you can pause the video. But long story short, you end up plugging in that parallax angle into this formula. The distance to the star is equal to 1 divided by the parallax angle, where the parallax angle is measured in arc seconds in this case. It can actually be measured in any units that you want, but if you measure it in arc seconds, the distance that you get is going to be in units of parsecs. That's the whole point. That's where the word parsec comes from. So a parsec being about 3 1/4 light years. So if a distant star has a parallax angle of 1/10 of an arc second, remember an arc second is 1/3600th of a degree, so if the parallax angle of that star over a course of a year is 1/36,000th of a degree, then we would say that that star is 10 parsecs away from us. That is about 32.6 light years. So again, Alpha Centauri is the closest star system to our Sun, and that has a parallax angle of 0.74 arc seconds. And remember how this formula goes. You have an inverse relationship, so the farther away the star is, the smaller the angle it's going to make. That's kind of common sense, but that also shows up in this formula, and it's inversely proportional. The distance to the star is directly inversely proportional to the parallax, not parallax to the second power, not square root of parallax, just inversely proportional parallax. And that's why I said directly, because it's parallax to the first power, but in the denominator. So for a very large telescope, there's a problem though. Because of turbulent motions in Earth's atmosphere, the sizes of stars themselves are in the order of 1 to 2 arc seconds. So it's difficult to use this method to determine parallaxes for stars. Sometimes, though, you can use various observational techniques to tease out some of this information, but generally speaking, it's hard. What you really want is a telescope that's in orbit. So what that means is that before we actually got telescopes into orbit, we couldn't really use parallax to determine distances to stars that were more than about 60 parsecs away. In fact, before 1990, about 1/3 of parallax measurements were actually made using the 26-inch refracting telescope at UVA's McCormick Observatory. So that's kind of a nice little local tidbit of information for me, at least, since I'm making this video from Virginia. Now, Hipparchus which was named after the ancient astronomer philosopher Hipparchus, except spelled differently to make it into an acronym: High Precision Parallax Collecting Satellite, Hipparchos. It was able to determine parallaxes for about 120,000 stars. In fact, we've gotten it more than that since then by reanalyzing Hipparchus data, especially also kind of combining with Hubble Space Telescope data. And Hipparchus itself, though, was only able to determine reasonably accurate distances out to 1,000 parsecs. So it could determine parallaxes to within 1,000th of an arc second. So there's where that 1,000 parsecs comes from, 1 divided by 1/1000th. Now, the Gaia spacecraft was launched in 2013 by the European Space Agency, and it's in the process of measuring very precise positions to at least 1.7 billion stars. In fact, it seems likely now that that's going to be extended because the mission has been quite successful so far. And it's going to measure distances out to 50,000 parsecs. Now remember that the diameter of our galaxy is about 120,000 light years, and we're about 27,000 light years from the center. So that'll get us distances to any stars that we can see in our galaxy, really. And accurate distances that, in other words, I think that's going to be to within like 1% accuracy, are going to be given for any stars within about 5,000 parsecs that it's able to measure. Now, there are some caveats on this that I'm going to get to soon, but we are going to get, in fact, we're in the process of getting accurate distances out to 5,000 parsecs, that is about 16,000 light years. So we've already had 2 Gaia data releases at this point, and this being right now March of 2020, and we're anticipating a couple of more over the next few years. So again, some of this stuff is review, but just some of the apparently brightest stars. Again, if you want to pause the video, then pause the video. I'm just going to go through these. And also how the inverse law propagation of light works, the idea that the apparent brightness of a light source, at least in terms of how much light we're getting from it, goes as 1 over your distance squared to the source. And using that, we can determine luminosities of stars if we know their distances. And in some cases, in particular, in the case of this star R136A1, we know its distance quite accurately through a method that we're going to discuss soon. But this particular star has a brightness of 8.7 million times that of our Sun, if you consider the light emitted at all wavelengths. Now, another star that we've discussed before, Eta Carina, has a luminosity of about 5 million suns. But Proxima Centauri, the closest star to our Sun, is only 50 millionths as bright as our Sun. So you need either a telescope or large binoculars to see it, in spite of the fact that it's the closest star to our Sun. Here is a picture of the R136 cluster. It's one of my favorite pictures, taken by Bob O'Connell at UVA, as well as a couple of other of his collaborators, but just a very nice, colorful picture, but shows the R136 cluster very, very well. And at the very center of that is the bright star R136A1. And that is one of the, actually it is the brightest star we know of and the most massive star we know of. So here's kind of a size comparison of some of the stars out there. So the yellow star is a model for our Sun, and here we have a nice bright blue giant star, and here we have a blue supergiant star in comparison. And then here is a red dwarf star. A red dwarf star isn't all that much bigger than the planet Jupiter. And I should also mention that red supergiant stars are way bigger than a blue supergiant star. So that's something to keep in mind, but that's not on this size comparison here. So now just talking about the apparent and absolute magnitude systems. We've discussed this before in class, and therefore I'm going to go through this really quickly. But again, if you need to stop and read the items, then just pause the video whenever you need. But we have our apparent magnitude system, which just telling us how bright things appear to our eyes. This was devised by Hipparchus. And the absolute magnitude system gives scale to the apparent magnitude system by saying, okay, let's just pretend that everything is 10 parsecs away. How bright would it appear to us on the apparent magnitude scale? So that would be its absolute magnitude. In fact, from that, therefore, there's a nice little formula for determining the distance to an object. If you happen to know its apparent magnitude, if you happen to know its absolute magnitude, and you've measured its apparent magnitude, then the distance to the object is equal to 10 to the power of the apparent magnitude minus the absolute magnitude plus 5 all over 5, that whole thing being the exponent, apparent minus absolute plus 5 over 5, that's all in the exponent. That 10 to that power of parsecs. So that's how astronomers can determine distances, in case you're curious. So anyway, long story short, fainter objects have greater apparent magnitudes, brighter objects have lesser apparent magnitudes. That is more to the left on the number line. Now, brightness. Brightness is the kind of everyday term for what astronomers think of as flux. And we've gone through this formula before. Brightness of a source is equal to its luminosity divided by 4 pi distance squared, where d is the distance to the object in that formula. So, if an object is twice as far from us, it's going to appear 1/4 as bright. We've talked about this before. So let's say you need to determine the distance to the Pleiades, and you happen to find a star in the Pleiades that you recognize to be basically the same type of star as the bright star Vega, whose distance we know very well because of parallax. So knowing the distance to Vega, it turns out we can determine the distance to that star in the Pleiades. So the idea is that if we're told that that star or if we measure that star to have 256 times fainter brightness than Vega has, then plugging that into the formula, we recognize that that star must be 16 times as far away from us as Vega, because 256 is 16 squared. So, since we know the distance to Vega real well, now we estimate the distance to the Pleiades that way as being 400 light years away. This type of method is known as main sequence fitting. We have an accurate way of doing this that we will discuss in a future PowerPoint. But, long story short, this allows us to determine distances to stars even if you don't have trigonometric distances to them. So there are other ways, though, that we're going to talk about very soon. Now, turns out the actual distance to the Pleiades is something like 440-something light years. That's something that was determined quite precisely recently with the Gaia spacecraft. Now, what about distances to stars that are more than 1,000 parsecs away? Well, nowadays the Gaia spacecraft is able to give us very accurate distances to stars that are 5,000 parsecs away. But what if they're farther away than that, and the accuracy of the Gaia measurements starts to diminish? Again, Gaia is going to give us distances to 1.7 billion stars, actually probably more than that, out to distances of about 50,000 parsecs, that is 160,000 light years, which is about the distance to the Large Magellanic Cloud. Well, to do that, we need something called standard candles, and this is where that distance formula ends up coming in. So there are certain types of stars that have known brightnesses, and these are known as standard candles. Now, this whole relationship was calibrated back a little bit over a century ago by Henrietta Leavitt. She was one of the astronomers at Harvard, and she calibrated the period luminosity relationship for Cepheid variable stars in the Large and Small Magellanic Clouds. I think she got both of them. I know she did it with the Small Magellanic Cloud, but I think she also did it with the Large Magellanic Cloud. And she was able to do this because of the fact that the size of the Magellanic Clouds is relatively small compared with their distances from us. At least the distances between the stars that we can see is reasonably small, so you can get a fairly good calibration that way. Nowadays we have better calibrations and everything, but again, this was first done a century ago. And the reason that this is useful is because some of these stars so-called Cepheid variables, these are quite bright when they are at their peak luminosity. They're so bright that this allows us to determine distances to them even when they're about 50 megaparsecs away. That is about 160 million light years away. So, standard candles. Well, pretend that all stars had exactly the same luminosity. Well then, the brightness of a star would only depend on its distance from us, as well as any sort of dust that might be between us and the star. That's something we have to take into consideration, but luckily that's something is easy to measure. We call that extinction, and we'll talk about how to correct for that later. But by measuring apparent brightness, in this case, we would be able to calculate the distance of that star using the fact that brightness is luminosity over 4 pi d squared, because again, if they all have the same luminosity, that means we know the luminosity. Of course, naturally, we're not so lucky. Stars have a range of luminosities, and they have a range of distances. But there are certain classes that have a small range of luminosities, or their range of luminosities is something that can be calibrated like Henrietta Leavitt did, and these are called standard candles. So let's consider an example. Let's pretend that that the brightest A-type stars, which we call A0 stars, have a luminosity of 55 times greater than the Sun. Well, we know that Vega is an A0 star. That goes on that OBAFGKM scale that we talked about when talking about stars and the types of stars that are potentially good places to look for extrasolar planets that might have life. So Vega is an A0 star. The number talks about like the brightness versus dimness. Like you know that OBAFGKM, well, an F star is going to be dimmer intrinsically than an A star. But how much dimmer? Well, you can divide the type A stars into 10 types. You have A0s, then A1, A2, A3, A4, A5, A6, A7, A8, A9, and after A9 is F0. And then you go through it again until you get to F9 and then G0, etc. Like our sun is a G2 star. So anyway, it turns out that it actually is true that all A0 main sequence stars, what main sequence means, again, that's a star that is doing what our sun is doing. It is currently fusing hydrogen into helium in its core. And why we call it main sequence, well, we're going to get to that in our next discussion. But anyway, suffice to say, it turns out that all A0 main sequence stars actually do have about the same luminosity. So if you find a star that you know to be an A0 star, then you can figure out really how far away it is based on how bright it is. So let's say you have a star that's identical to the sun, that would have a visual magnitude of 0.0 if you placed it at a distance of 1 parsec. Well, how far is Vega from the Earth? Well, Vega is giving off 55 times as much energy because that's what A stars do compared with our sun. So therefore, it must be 7.4 times farther away than 1 parsec. So that would put it at 7.4 parsecs, which is 25 light years. Where did I get that 7.4? 7.4 is the square root of 55. So it's, remember, luminosity goes as, or sorry, brightness goes as luminosity over 4 pi distance squared. So, what about variable stars? Vega is not a variable star, but there are things called variable stars, stars that fluctuate in brightness, and it turns out that Betelgeuse, for example, is a well-known variable star, but it's not the type that we're looking for in this case. So, here's the deal. So we've talked about hydrostatic equilibrium before, this balance between the outward push of pressure and the inward pull of gravity in a star. Well, when a star goes into, at least when a lot of stars, especially the massive ones, go into their giant phases after they're done fusing hydrogen into helium in their central cores, they end up overshooting as they start to expand outward, and they have these kind of instabilities. And the result is that by overshooting, it's like, okay, they go farther out than what hydrostatic equilibrium would maintain, so eventually gravity ends up pulling them back, and then they end up getting compressed, but again, they overshoot that, so then pressure ends up forcing them back out, and the cycle repeats. Well, this happens for lots of different types of stars, but it happens in a certain way for stars called Cepheid variable stars. And we call them Cepheid variables because they have a certain type of pattern that is similar to that of the star Delta Cephei, which is a certain star in the constellation Cepheus. And that pattern, this magnitude versus time, is known as a light curve. And there are certain vocabulary terms here. For example, you have the minimum brightness, the trough, you have the maximum brightness, the peak, and you have the time between peaks, which is known as the period. That's also, of course, the time between troughs. So this is a representative light curve for Delta Cephei. So the period, though, is what we are interested in, because what Henrietta Leavitt did for us was she actually she calibrated a period luminosity relationship. She found a logarithmic relationship between a star's period and its luminosity by examining these stars in the Magellanic Clouds. And it turns out that from that we realized that these Cepheid variables have luminosities that are between 1,000 and 10,000 times bigger than that of our sun, and they have periods of 3 to 50 days. And this variation in luminosity versus this period, it's a relatively small percent. If you know a star's period from that light curve, then you can determine its luminosity to within a few percent. Well, that's impressive. That allows us to get its distance correct to within about a few percent or so. Now, I will mention that there is another famous Cepheid variable star. That is a star called Polaris, the star in Ursa Minor that you had better know. So, in any case, yeah, here's the constellation Cepheus, and again, the brightness of Delta Cephei. So from this, you can see that the period of oscillation, so to speak, for Delta Cephei is about 5.4 days. And that's something that you can plug into the period luminosity relationship to determine the brightness of Delta Cephei. Oh, and by the way, this star right here is Delta Cephei. Oh, whoops, sorry, never mind. It's the one that's labeled right here. There's Delta Cephei. So there's kind of the crown of Cepheus. And I was at first thrown off here because usually the way that Cepheus is drawn includes the star Delta Cephei as opposed to the star right here. By the way, this star right here is Herschel's Garnet star. It's a very, very big, massive star. It's one of the other biggest stars known. If you put it in place of our sun, its outer layers would go out to about the orbit of Saturn. So, again, we talked about how Henrietta Leavitt discovered that period and calibrated that period luminosity relationship. And the brighter Cepheids always have longer periods. Why does that make sense? Well, a brighter Cepheid is probably going to be a more massive Cepheid variable. And think about an object oscillating from a spring. If you put a mass and hang it from a spring, well, if the object is more massive, the period of oscillation when you shake the spring up and down, the natural period of oscillation is going to be longer if you have a more massive object at the end of that spring. Why? Because of Newton's second law, force equals mass times acceleration. So a bigger mass, given the same force, is going to undergo a smaller acceleration. So therefore, smaller acceleration means that it's going to take longer to change its velocity, which means longer to complete one full cycle. So a bigger mass is going to have a longer period. So that's why that should actually work, just in terms of a physical mechanism. What Henrietta Leavitt did is she just calibrated the data and just worked with what the data showed her, but we understand that these data actually make sense also. Now, if you make what we call this logarithmic plot, then you end up getting a pretty straight line here. Notice that there are other types of variable stars called RR Lyrae stars. These are all kind of in the same group. If you get an RR Lyrae star, you pretty much know what its luminosity is. But with the Cepheids, you have to draw a straight line through these data, and from that you calibrate your period luminosity relationship. So here's an example. If you have one Cepheid variable with a period of 30 days and another, a period of 3 days and another with a period of 30 days, it turns out that the star with a longer period is 2 magnitudes brighter, which means 6 times brighter if you do that 2.513 squared. And in fact, it's a little more than 6 times, but we're rounding here. So since all stars are in the same stellar system, they are all the same distance from Earth. So if you have a cluster of stars that has a Cepheid variable with an oscillation period of 3 days, you know that that cluster of stars is therefore a certain distance from us. So, and indeed, most stars exist as part of multiple star systems. Now, in some cases, that cluster of stars happens to be a galaxy. And if you can discover a few Cepheid variables in a galaxy, then that can often give you a relatively accurate distance determination to that galaxy, assuming that you have an accurate brightness calibration for your Cepheid variables, which is something that is being significantly improved right now with data from the Gaia spacecraft. So, at that time, though, when Henrietta Leavitt calibrated these data, the actual true distance to the Large Magellanic Cloud and Small Magellanic Cloud, those distances were unknown. But nowadays, we actually know that quite well. There was a supernova that went off in the Large Magellanic Cloud in 1987. At least we saw its light in 1987. And using some geometry from that, we got the distance to that very precisely. It's like 162,000 light years, if I remember correctly. But it used to be the case that we did not have any direct distance measurements to Cepheid variables with parallax. But now the Gaia spacecraft has measured a lot of Cepheid variables and also a lot of RR Lyrae stars as well. But before that time, astronomers needed to find distances to a few Cepheids to try to determine their luminosities. But now we have distances to a whole lot of them, so we are in the process of getting a very good period luminosity relationship as a result of that. So now, a little bit more about these RR Lyrae stars will be stated soon. But let's assume that I found a Cepheid in the Large Magellanic Cloud and it has a period of 10 days, an apparent magnitude of 14.8. Well, knowing that our Sun, from the distance of the Large Magellanic Cloud, knowing that the Sun would have that same apparent magnitude at a distance of 1,000 parsecs, what's the distance to the Large Magellanic Cloud? Well, using that figure and in other words, just putting in 10 days here, we see that this thing is about 1,000 times or so the luminosity of our Sun. In fact, it turns out, if you really look at it real closely, it turns out to be 2,500 times the luminosity of our Sun. You determine, remember, luminosity goes as, brightness goes as luminosity over 4 pi distance squared. So we realize this thing is 2,500 times brighter than our Sun, and given the or brighter than what our Sun would appear at a distance of 1,000 parsecs. That means that this thing must be square root of 2,500, 50 times farther away than 1,000 parsecs. That is 50,000 parsecs. And again, we have a much better distance than that with like a 1% error based on geometry, which we'll discuss at a later time. But anyway, nowadays, Cepheid variable stars, we're actually capable of using them potentially out to about 50 megaparsecs using the Hubble Space Telescope. But we actually have galaxy distance determinations that are relatively good, out to about 60 million light years, in other words, the other side of the Virgo cluster. In fact, that was one of the main scientific missions of the Hubble Space Telescope when it went up. It was to find distances, or find Cepheid variable stars in other galaxies so that we could determine the distances to those galaxies, and from that determine the rate at which our universe is expanding, something that we'll discuss in a bit more detail in a later day. So here's a zoom into one of the galaxies out there, the 100th object in Charles Messier's catalog of fuzzy things that aren't comets, M100. And I think we found several Cepheid variables in M100, and this is kind of a zoom in on one of those and how its brightness changes over a number of days. And based on that period, and based on its brightness when it's at its peak, we can estimate the distance to M100. In fact, here it is over a number of other days. In fact, I think this is a different star. Now back to those RR Lyrae stars. We notice that they kind of form a group of stars and of relatively similar luminosities, and we actually have a number of these that have been found with the Gaia spacecraft. The Gaia spacecraft has found over 140,000 of these. So once all of these data get analyzed, we should have a very good period of luminosity relationship for the RR Lyrae stars. So that's something else to look forward to. So next time we will discuss what is really going on with a star's color and what it means for the star's life. So hope to see you then.